Okay, so yes, welcome back to school. Spring quarter. This is our first week. I have a feeling it will fly by. And then we got a lot of exciting things, right? Data Fest is coming up. You guys are all registered for Data Fest, yeah? You should be. I mean, you're in Stats 102C. There's no reason you shouldn't be in Data Fest, and then you'll graduate. A lot of you. Some of you have more time, but that's that. Okay, so let's talk 102C and okay, and we'll get started. Okay, so 102C, this is Monte Carlo methods. And I think we'll have a good time. I have not finalized the syllabus. Okay, it's a big struggle. Every time I have a quarter, I feel like that parts of it went well, and certainly parts of it did not go well, or did not go as planned. And so I'm trying to figure out how to weight the different assignments, how to weight the exams, and that's what's holding me up on writing my final version of the syllabus. I want to, so let me just share my vision or my hopes and dreams, but then they always get tempered by reality, and it's always a little bit heartbreaking. So anyway, I want your time in this class to be enjoyable, and I want to reduce the amount of stress that you guys have. And so for me, that means getting the exams to be worth like weight them less. So it's your entire grade's not based on one midterm and one final. I know a lot of classes work that way, and that's totally fine. But for me, I like to weigh those a little bit less, just in case you have a bad test day or whatever. It doesn't ruin your life. But that means other things have to be weighted more. And so I like seeing students in class. So so for me, attendance is a valuable thing. Last quarter, I tried to do attendance, and I was disappointed by what happened. In that people were not being honest about their attendance, and so I want to try it again. Okay, I want to try attendance again, but this time I'm going to put in a harsh warning, saying on not random, but arbitrary days. I can't use the word random because it's not actually going to be random. But on arbitrarily selected days, I might actually do roll call after people say whether they're here or not, and if I catch you lying to me, then you'll lose a lot of points. I'll have to finalize the verbiage on that. But basically, because last quarter attendance was self-reported. It was kind of like, if you're here, tell me that you're here. But then people said I'm here when they actually weren't here, and so I guess that was my bad for trusting. Right. 80% of you were honest, or 80% of the students were honest. Homework. I weighed the homework more, and I think that's good. I had a take-home final last quarter, and there were some problems there, and so I have to rethink how to do kind of these final evaluation methods, and so that's why I haven't posted a final syllabus. I'm trying to figure this out. If you want to give me some feedback or give me some advice and counsel, I would happily hear you guys out. My goal is to have the assignments of learning value. Okay, so I think that's why I've weighted the homework more. I know, and with the homework, I've encouraged students to work together. there is always maybe a possibility that students just copied each other's homework without actually learning themselves, and that's really hard to prove. And so I generally don't threaten, I don't know, disciplinary action for homework. But for the final, that was sad for me. So, but anyway, sorry, I don't mean to be sharing my woes as a teacher with you, but I just want to kind of tell you where I'm coming from, and so for me, I value honesty and hard work, and you know, I try to make the homeworks are worth a lot, but one of them individually is not going to cause you to fail. And so I would much rather have students attempt, do their best, and if the student can't figure out how it needs to be done, to just submit it as is without resorting to yeah, I guess copying, I guess is, is what I want. So anyway, I'll try to get this sorted out, and I'll get the syllabus posted. So, but I apologize that no syllabus has been posted. Maybe some of you are asking about textbooks, things of that nature. I think we will use a text. It will be available for free online from Springer Link, and so I'll post the links for that online. And but today's lecture, we don't really need a textbook to get started. So okay. Any questions or issues before we continue on? No, we're good. Okay. Well, it's good to see a lot of familiar faces. Some faces are new. Oh, I was thinking of doing this, and you might say this is the dumbest idea ever, but and now I'm embarrassed to share it. But all right, you guys are going to graduate soon, and I think some of you have been like sitting next to some people like for the last year, and you still don't know their name. And I also realize that this is a problem that I have, that I've there's a lot of faces I recognize, but maybe I have some trouble with names. So this will be kind of like an opt-in thing, or I don't know, maybe it'll be worth like 1% of your grade. I think I'll have you guys upload a selfie, okay, with your name, and then I'll try to learn all of your faces and names, and then if you want, and this is the optional part, we can make the selfie something that is quote shared with the class, okay, and so then you can learn your classmates' faces and names, all right, enhancing a little bit of the sense of community that I feel like we should have in the statistics department that maybe doesn't yet exist, okay? I know there's like the stats, UCLA stats Facebook group, and then there's the memes page, and so this is entirely optional. I mean, if you don't want other students to know your face and name, that's totally fine. I won't require that you opt in to share it with the group, but I'd like to. I mean, I have the roster that UCLA provides, but these are like your freshman pictures, and needless to say, some of you look different today. Not in any bad way, but just you look different from when you were a freshman to when you're a senior. So anyway, we'll. I guess that will be part of your first week's homework, and we'll do that. And then of those who opt in, I'll compile a little PDF or something if you guys want to learn each other's names and faces. Okay. All right. I don't know. Is that silly? A little bit. All right. A little bit silly, but this is what I want to do. Okay. All right. We'll get started. Okay. Monte Carlo methods. Okay. So, oh yes, question.
Will you also be uploading a selfie?
I can upload a selfie if you want me to upload a selfie. All right. But okay. Yeah. And I want it to be like, don't make it like a glamour photo where, it doesn't have to be your perfect selfie. Just like an everyday, like I want it to be like taken within the last week or today or something. Doesn't have to be. You don't have to be standing in front of the Golden Gate Bridge or something. Okay, let's talk Monte Carlo methods. All right, so we've actually covered some Monte Carlo methods in 102A. If you took 102A with me, maybe if you didn't take 102A with me, you might not have covered Monte Carlo methods. But if you had to program Monopoly, that is that's a Monte Carlo problem. Okay, and the idea behind Monte Carlo methods, the big idea is that there is a problem, a probability related problem. I can't spell. And this probability related problem perhaps is too complex to be solved analytically. Okay. It may be the math and the equations, maybe they just get too messy. Okay. And so our attempt to solve will to will be our attempt to solve will, I'll say, use either simulation or just multiple random draws from the probability distribution. Okay, and by doing many random draws from the thing that we're interested in, we can gain insight to answer this question. Okay, this original problem, which was too complex to be solved analytically, we can solve through simulation. Okay, and so if you didn't do the Monopoly problem, no worries. Okay, the premise for the Monopoly was, we have a board game, and we are just curious which spaces on the board get landed on most frequently. Okay, so it's a board game, and we want to know which spaces are landed on most frequently. And technically, we can answer this question analytically. Okay, we can create, maybe we'll cover this later, what's known as a transition matrix. There are 40 spaces on the board, and we can create a transition matrix which shows if you are on space 1, what is the probability that your next state, that you will transition to space 2, right? And if you're playing Monopoly, if you're on space 1, there's 0 probability of moving to space 2 because you're rolling 2 dice, and so the smallest number you can possibly get would be a 2, and so there's no chance of going to space 2. Okay? However, there is a transition probability of going from space 1 to space 3, and that probability is 1 in 36, because out of the 36 possible roll combinations, one of those will land 2, and so you have a transition probability of going from space 1 to space 3. And we can set this up for the entire board. We can take into account all of the different rules and set up the complete transition matrix, and we can use the transition matrix to determine what's called the stationary distribution, which means if we run this transition matrix over and over and over and over again, eventually it will come to a certain probability distribution that is stationary, meaning this reveals the true probabilities where everything balances out, and this will reveal which spaces are landed upon most frequently and which ones are landed upon least frequently. Okay, I just kind of gave you this high overview spiel right now. Don't worry if all of that didn't make sense. The answer is the point of that thing was just to say that if we wanted to do it analytically, we could do it analytically. Okay. However, there are situations where it's even more complex and we can't really do it analytically. Okay. And so in these cases, sometimes it might be easier to try to implement all of the rules as chunks of code, and we can run simulations of this code to say, hey, I'm on space 1. I'm going to simulate rolling a die. I'm going to then simulate moving my piece to a new spot. And then, if there's special rules that apply, I'll simulate applying those special rules, and I'll see where I end up. And we can do this thousands of times and also get an idea of which spaces are landed upon most frequently. Okay? So which spaces are landed on most frequently? Okay, so the analytic approach will be to use transition matrices. Okay. Have you guys encountered transition matrices before, or is this? Okay, I'm seeing mostly. Okay, it'll probably be worth a small detour to cover it. Okay, and then and the other one is the Monte Carlo approach. And this is to run a simulation. Okay, this one will give us kind of the theoretic, and this one will give us an empirical probability, but they will both provide insight as to what the answer is. Okay. We have, it's not just running simulations for board games. In general, in statistics, we encounter problems kind of the form, a lot of times we want to know what is the probability distribution. Okay, so sometimes we have a few, okay, so we might wish to know the probability distribution of some phenomena, okay? Okay, or a lot of times we wish to know the expected value of the probability distribution. Okay, so the probability distribution would be kind of our, maybe I'll just say P of x. And we might wish to learn the expected value of the probability distribution. So this would be E of x. And how do we calculate the expected value of some probability distribution? It's the integral from what? Minus infinity to infinity of x times P of x, right? dx. So this is often what we want to do, okay? Or frequently, or we might want the expected value of a function. Okay, want the expected value of a function. We'll say f of x of the random variable x. Okay, and so this would be expected value of yeah, I guess that would be expected value of f. And how do we calculate this? It's the integral negative infinity to infinity of f of x times p of x dx, yes? I'm hoping this is familiar. Okay. If not, please review your, I don't know, mathematical statistics stuff, 100B. Okay, and so a lot of times this thing or this thing, any of this, it might be complicated, okay? And we might not have a functional form of p of x, okay? Or this integral might be too complicated to calculate itself, okay? So either maybe p of x, we don't have a functional form, or maybe we do, or taking the integral, because integrals are hard, right? Taking the integral of this product of functions, this might be too complicated to do, okay? So many times this integral is too complicated for an analytic approach. Okay, and so we'll use a Monte Carlo method to get at this. Okay, a lot of times this p of x is, if you do anything with Bayesian statistics, and we'll probably have to spend time talking about Bayesian statistics, you might have some probability distribution p of x that is the posterior distribution between which is the result of your prior distribution multiplied by your likelihood, right? Or your likelihood times your prior divided by the marginal. That gives you your posterior distribution. And a lot of times these things are complicated, okay? What do we do, right? So, lots of applications, okay? I don't know if I have to cover all of this, okay? But, we have, so we'll say, well, okay, so this is probably one of the biggest applications, okay, for Monte Carlo methods. Probably is in Bayesian statistics, okay? And so we'll probably have to spend a little bit of time reviewing Bayesian statistics, but the idea is your posterior distribution is equal to your likelihood times your prior divided by the marginal. Okay, so this would be the probability of kind of theta given your data x. And this thing might be complicated, okay? Perhaps too complicated to integrate as part of expected, in this case it would be expected value of theta. Okay. So our approach to kind of get at this will be to use a Monte Carlo approach. Okay, and so kind of the biggest idea here is we're going to take random draws from this probability distribution. Okay, we're going to draw random values from the probability distribution, and we'll use that to get an idea of what the integral is looks like. Okay, so so we'll say you know, we want to know. Let's say we want to learn the expected value of some function which we have defined as the integral from negative infinity to infinity of f of x times. Okay, and so this is kind of the Monte Carlo approach. And that is, we will draw samples we'll draw samples from, I guess we'll define my samples as, let's see, the vector x L, okay, where L is equal to 1 through 1, 2, up through L, okay, capital L. And we're going to draw samples of x from, let's say, from P of x, okay? And therefore our estimate kind of the estimate of the kind of the expectation, okay? So in this case, we would have f hat. This is equal to 1 over L, and we sum from L equals 1 to capital L of x of each draw. Okay, so basically we're going to take, let's say 1,000 random numbers from P of x. Okay, so so kind of just illustrate this, so we will take 1,000 random numbers drawn from the distribution P of x, okay? And then we calculate f of each of those numbers, all right? For each value drawn. Okay? And then we take the average of all of those f's, okay? Okay. Does that kind of make sense? All right, so let's maybe we can illustrate this with an example. So we'll do an example. All right. This might. Let me see. I hope I don't have anything. Okay. So I'm going to kind of do this. I'm doing this on the fly live, and so there's a great possibility that the code doesn't work. Okay. Let's say we have the function f of x is equal to, we're going to take x and we're going to square it. Okay. And let's say x comes from the normal distribution 0, 1. Okay. What is does this sound like anything? It's the chi-square distribution, right? Okay, if x comes from a normal 0, 1, this is, and if we're looking at x squared, okay, this is going to give us a chi-square distribution with 1 degree of freedom, right? So this kind of, so if we say, if this is our distribution, this is the chi-squared distribution with 1 degree of freedom. Okay, so let's say, you hadn't, let's say, I don't know, you don't have Wikipedia or something, and Wikipedia chi-squared. The chi-squared distribution will go, all right, and then so let's say you're like, oh, I don't remember what the mean of the chi-squared distribution is and all of this, okay? So let's, so what we can do is, let's say we want to estimate, what is the mean of this chi-squared distribution, right? So what is the expected value of f, all right? So this is going to go from, well, we'll go from negative infinity to infinity of basically x squared times p of x dx, okay? Where p of x is the normal PDF, which I should have this memorized, but I don't. Which is this thing, okay? 1 over 2 sigma squared pi times, what is it? E to the x minus mu over 2 sigma squared. What's going on here? Okay, so that's what we have. Okay, so what I'm going to do is I'm going to just we'll just take 1,000 random numbers. Okay, so so the Monte Carlo method to estimate this. We will draw 1,000 values from normal 0, 1. Okay, then we will square each of those values. And then we will find the mean. Of those, 1,000 squared values. I mean, and technically, if we wanted to, we can create a histogram of these 1,000 squared values, and that would give us kind of a histogram of the chi-squared distribution as well, right? So this is like the most basic form of Monte Carlo methods that we can do. So I can just say we're going to say x is going to be random normal, we want 1,000 values, right? We can say 0, 1, but that's also default. Okay, so we can do that. I've got 1,000 values of x. I can say, you know, give me a histogram of x. We'll say breaks equals 25. There is the 1,000 values we've drawn. Okay, and then I'll call this z. Technically, I should do z is this, and then this should be x squared will be z squared. Okay, so we'll do z is that, then we'll do that. Okay, and then so now I can do, you know, what's the histogram of z? And we'll do breaks equals 25. Okay, well, that's not what happened. Huh? Oh, duh. Thank you. Okay, so this is let's chi-squared with 1 degree of freedom looks indeed like that. Okay, and then we can just say, you know, okay, what's the mean of x squared? All right, and we get 0.9919. Okay, and that sounds very much like the what the mean of a true chi-squared distribution with 1 degree of freedom, which is 1. Okay. All right, and so, you know, I mean, we obviously wouldn't do this for the chi-squared distribution because we know the properties of the chi-squared distribution. It's already been solved for us analytically. But this is kind of just, I don't know, a broad illustration of where we're headed. Let me, I guess I'll histogram of z. We'll do breaks equals 25. So we'll do this, and I'll just take a screenshot of this. I don't think it's worth uploading a script just for this chunk of code here. So if you're curious how to do it, there you go. Okay, so you know, as far as the rest of the course goes, there's we've got to talk about random number generation a little bit. Okay, so so I think, yeah, this week we'll talk about how the computer comes up with random numbers. Well, I don't know about the how. We'll just say it happens, okay? And I'll link you some videos. There's like this. Okay, we live. I don't know what I'm trying to say. All right, pseudo random number generation. This is kind of solved. Okay, so we've got this, PRNGs. This is a solved problem. Okay, so PRNG. This is pseudo. I'll just link a video for you guys to watch. Okay, random number generation. Okay, this is practically solved. Okay, and so I don't know if it's worth spending much time in it, right? Like back in the day, if you took computer science, you had to learn how, you know, the adding machine worked, okay? And you had to learn how, you know, at a very base level, how the bits and ones and zeros worked. And today we don't really bother it because it's all kind of been solved. I mean, I guess if you're computer engineering, you gotta learn this stuff. Pseudo random number generation, you know, a lot of times we just say, hey, we can take, we can do R unit, okay? And this generates, you know, this generates values from 0 to 1, okay? Generates random values from there. They're random numbers. It's great. if you go to R and you just say, hey, give me a random number, it does it. This this used to be a complicated thing, and people spent 30 years ago a lot of time, people were working on trying to figure out how to get good random number generators from a computer, right? Because a computer is deterministic. It should not behave in a random way. Every time you do something, it should give you the same results. But a lot of times for these kinds of studies, random numbers are a useful thing. And well, there's a philosophical question of how much of the universe is random, and it seems maybe at the quantum level there's actual randomness, but outside of the quantum level, I don't know, everything's deterministic, right? If we knew exactly, for all intents and purposes, we treat coin flips as random, but if we knew exactly the angular momentum and the velocity at which it takes off, and the I don't know, the properties of the surface on which it will bounce, we might be able to predict how coin flips will land. But with random number generators, we use something called the Mersenne twister. You can look this up. It's really complicated, okay? I've tried to read it and try to fully understand exactly how it's working, and I don't fully understand how it works, okay? But you can read up on it. Basically, this is kind of the gold standard now. This is our kind of our new gold standard for random number generation. It is not cryptographically secure. If that is of interest to you, if you want to generate random codes to I don't know, like for passwords and stuff, a lot of times random components are used there. It's not secure, and you can predict what will come next if you know, if you can figure out your seed values. So in that case, the Mersenne or Mersenne twister is not good. But as far as giving us values from 0 to 1 that have no correlation with previous values and things like that, it's very good. There has been what is it called? A linear congruential. I forget the full acronym. Linear congruential generator. This used to be how we generated random numbers. This has fallen out of favor because the Mersenne twister is far superior. But as far as the history of random number generations go, the linear congruential generator may be of interest. Okay. I'll post a link to YouTube that has some good, I don't know, insight on here. We won't worry too much about getting the 0, 1. Okay. But once we go from 0, 1, we can talk about, well, how do we then get random normal numbers? Okay. We kind of take for granted that we can just do our norm. Okay. And there's actually some math involved here. And perhaps, well, not perhaps, part of the course will be, how do we generate random numbers from a distribution that is not our quote standard, one of the standard distributions. If it's not a random normal, if it's not a random gamma or binomial distribution from which, we have these built-in things in R, how do we generate random numbers? Because effectively that's what we're trying to go for when we do the Monte Carlo methods, right? We want to draw random numbers from some unknown probability distribution. How do we do that? Okay, well, it's going to come back to using the pseudo-random number generator, the RUnif, as kind of a base, and to operate from there to get other things. Okay, and so that's where we're headed. I'll try to find some interesting applications for all of this, and that's what we got. So we'll wrap up here today. Looking forward to a great quarter with you guys, and we'll see you guys on Wednesday. Important. there's some confusion about who our TA is, okay? One source says it's this person, another source says it's another person. So we're going to try to get that sorted out. For now, no section tomorrow, okay? Because section is scheduled for Tuesdays, right, in this class? Yeah. So no section tomorrow until we get all of this TA stuff figured out. There wasn't going to be anything of great importance covered anyway, so we're okay.